Okay, so next up, we're going to try to go the reverse direction of this little Fermat's result. So down in front, you should see the chicken scratch that I wrote from the last video, which was the forward direction. So I assumed I had the decomposition, and then that told me that P was a 1 mod 4. Well, now I want to do the reverse direction, which is actually the more interesting one, is that if you test my prime against the 4, if it's a 1 mod 4, then I know that there will be a decomposition. Whether or not I know what those values are is going to come back to the actual algorithms that we have to study a bit later, but that's the more interesting of the two directions to actually study. The thing that's going to help me out a little bit are going to be some of these quadratic residues and quadratic non-residues. So there's a little bit of old school math 436 or this number theory and crypto stuff circulating in the back of your brain. So the claim that I want to lean on is that if you give me a prime that is a 1 mod 4, what I'm going to claim is that there is essentially a square root of -1. That is, I can solve this little equation of u squared equals -1 mod 14. If you don't like negatives, you can move that little negative over to the left, and we're going to see that we'll be able to find some u that when I square it and add a 1, it's actually going to be a 0 mod 13. The P being a 1 mod 4 actually has some of the more annoying versions of computing these square roots. The P's that are a 3 mod 4, we had a really nice shorthand kind of square root thing for that one. It was really easy to compute. In the event that my P is a 1 mod 4, that's where it branched out and we had a couple of different techniques. So the big story here is that there will be a U. We might just have to test a few different things to actually find that. So we'll see that in later implementations, but in the actual theoretical part of this, it's going to be that we have it and we can go with it. So the example that I want to lean on as we jump into this process is going to be the number 13. So P being 13 is prime, and it is a 1 mod 4 because it's 12 plus 1. Notice that we can actually come up with a U for this thing pretty easily. If I take u to be a 5 and not erase it, but if I take u to be a 5, if I square that 5 and add 1, you get a nice little 26, which is absolutely a 0 mod 13. So that's this result of this lemma, is that I have a prime. I'm claiming that there's a u that would satisfy this equation. Here's me giving an example of such a u. Well, because there's a square, we could technically take plus or minus this thing. So 5 would work. So would -5. And if I want to not deal with negatives, -5 modulo 13. So if I go on this little clock, so backwards 5 hours is the same thing as forwards 8 hours on a 13-hour clock. So 8 would also totally work. And if you studied 8 squared plus 1, you get 64 plus a 1, which is 65, which again is divisible by 13. So it's going to kick out a nice little 0. Officially, there are going to be some ways that we can try to find some of these things. So the expression that we're going to be studying is going to be something like this. So we're going to feed in various bases, and we're going to raise them to nice little exponents. And then the hope is that this thing is actually going to be one of these square roots of -1. The A value is the thing that we might have to cycle through and test various things. But we usually start at 2, and if that doesn't work, then we go up to 3 and so on from there. So for P being 13 and A being 2, this quantity, if I evaluate it, is going to become my 8. So that would have given me that 8 that we saw up here. So the 5 and the 8 that I have here are easy enough to compute and just test because there's only 13 things that I would need to test, but there is a little bit more systematic way that I can find that possible U as well. So we're looking for these non-residues, and later on we'll have a little reminder of what that actually looks like. But for now, that's the thing that I want to have in the back of my head, and that's going to be part of the actual argument for the reverse direction. So when we start this thing up, that's exactly what I'm going to state right off the bat. So I'm going in this direction. So I assume this stuff. I want to work backwards. So most of the argument, I'm going to keep just the 13 around. Occasionally, I'll change the 13 just into a prime P, but the argument's basically the same. So if you want to do it in a general format, you can kind of write it off to the side as I go. If you want to do it with 13s and 5s, that's totally cool as well. So I'm going to run with this example of 13, which we already know has a decomposition of 2 squared plus 3 squared. The goal then is to kind of think about where the 2 and 3 are actually going to be coming from. So for this 13, based off of that previous lemma, I know that there's going to be a u that satisfies this equation. U squared is 0 mod 13. I'm going to, for now, just use the 5 because it's smaller than the 8, but I could have used the 5, I could have used the 8. I can use any u that would satisfy that little equation. So from there, I'm going to begin building an actual lattice. I used an M when I should have used a U. So my lattice, again, is going to be this collection of a whole bunch of random little dots. So we're going to have these nice little weaving patterns that are going to emerge. And for this, it's going to be a lattice in 2 dimensions. I'm going to have 2 little vectors that are going to give me my kind of initial directionality. So I'm going to have a vector v1, which is going to be achieved by taking always a 1 in the first argument, and then whatever that little u was in the second argument. So it's going to be this little vector 1, 5. So over 1, up 5, and then anything along that little line that has integer weights as well. The other vector is basically going to be how much I'm just going to go up in the y direction. So vector v2 is going to be 0 always in the first slot, and then my prime p in the second slot. For this example, I'm then going to see the ordered pair or the vector 0, 13. So my lattice is then going to be any possible linear combination of those little things. So we get my initial 2 vectors. They essentially be kind of corners of these nice little parallelograms, and then I'm going to basically spam this thing out over the entire little grid. So we have a couple points drawn here. So we have my origin, which is 0, 0. I have vector v1. I have vector 2v1. I have vector 3v1 by taking integer multiples of those things. So you get these little chicken pox dots along the way. So we're not going to have the things between them, at least not initially, because I'm not going to take fractional weights of these things. It's always going to be integers. I'm going to have this integral lattice. So integers up along that way. We also have v2, which would go up that y-axis. So 0, 13. I would also get 0, 26, in that I can take multiples of that thing as well. And then you can start to crisscross these things a little bit as well. So I can have vector v1, and I can add vector v2 to it. So I can go v1 up to v1 plus v2. And the way, again, I add these vectors is just component-wise. So the 2 x values, so the 1 and the 0 makes a 1. And then the 2 y values, which are a 5 and a 13, make the 18. In these little lattices, I don't care which direction you add. So I can go v2 plus v1 or v1 plus v2. Either way, I'm going to end up at that top little corner. You could also take, vector v1, v2, and then you can add, or you can take 2 copies of v1. So v1, v1, and then go up v2, and you'd get another dot up there. You can go up, 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 and you can start to get this kind of little framework of things occurring. So that's the, at least, really bad picture of what this lattice is going to look like. It should have more dots on it, obviously, but I got lazy and ran out of room. It's tricky because I have, index of 0s and 1s and 2s and 3s on the bottom, but because the p was 13, the y-axis gets stretched out or compressed a little bit more. But you get this as kind of the general lattice that we want to actually work with. So that's our big goal. Before I jump back into the actual argument, there's one more fact that we're going to need to lean on. So this video is kind of like setting up the facts that we need. The first fact was that there was this little u. Once we have this u, we're going to build up the lattice. So we have this little lattice. Our future goal is going to be to identify some points that are going to be close to the origin. So v1, you could think about as being pretty close to the origin right off the bat. The distance from the origin to that thing, though, is about 5. So if I were to compute the length of vector v1, and if I compute the length, let's say squared, so it would be, well, let's just do the actual length. So it'd be the square root of the component squared. So 1 squared plus 5 squared, which is about the square root of 26, which is about 5, which is kind of big. It's not super duper small. We can actually find some vectors that are going to be closer to the origin than that thing, namely this little vector down here at 3, 2. So I can get to vector 3, 2 by taking 3 copies of vector v1. So that brings me up to 315, and then subtracting off vector v2. So 315 minus 0, 13 leaves me at 3, 2. And the length of that thing is really nice because it's going to be 3 squared plus 2 squared, which is the square root of 9 plus 4, which is the square root of 13, which is definitely less than 5. So it's closer. But more importantly, if I square all of this stuff, you get exactly that decomposition that we're hoping to see later. So that's the early spoiler alert stuff, is that this whole argument is going to boil down into trying to identify a vector that's close to the actual origin, closer possibly than that vector v1 happens to be. And that's going to connect back to these old school fundamental parallelograms, these parallelepipeds, if I do it in higher dimensional settings. So anytime we have a lattice, we're going to have one of these fundamental parallelograms. If I go back to this little picture, you can kind of see it sketched out in these little blue dashed lines. So it's that little shape that's generated by the vector v1 and the vector v2, and then I connect them to having the sum of them. So that little thing has an area. In higher dimensions, it's going to have a volume. And the volume of that thing is actually going to be connected to some circles that must contain a point. And that's going to be this Minkowski's theorem. So what this claims is that if this fundamental parallelogram of this lattice has area V, so whatever that number happens to be. In our example before, that area is going to be 13. Then if you construct a disk starting at the origin that has a set radius, so here the radius of that thing is going to be r, as long as the r satisfies some bound that's based off of the area, so it has a certain size, then that disk is guaranteed to contain a non-zero lattice point. So you can think about starting at the origin and then working your way out. And it's if you make this little radius big enough, eventually you will find a lattice point. It might be the vector v1, it might be vector v2, or more often than not, it's going to be something else that you're going to find as well. So here we're going to essentially set the stage for how we're going to do this actual proof. Is we're going to very cleverly build a R value. We're going to say that this random little ring is going to contain a non-zero lattice point. And guess what? That non-zero lattice point is going to have an X and a Y term whose square is going to be exactly the prime that we're looking for. Exactly like we saw here. We had the 3 and the 2. Well, 3 squared plus 2 squared, voila. That's in fact going to be the little 13 that we are hoping for. So I'm going to pause it here, and then we'll jump back actually into the argument and see some of those things unfold, and we'll come back. So give me a sec to pause it and jump back in.